So this lesson is fun. It's hard if you miss out on something, okay? So make sure you're paying attention, okay? But we're going to find volume of some really funky shapes. Now, just real fast, do you guys remember how to find the volume of, let's say, a prism? Prism. Length times width times height, right? Okay. What's the volume of, let's say, this guy then? Let's say it was a triangular prism.
Okay, yeah. 1/2 base times height.
So it'll be 1/2 of length times width times height. No, but I want to make this point, and this is important.
Mr. Bundy, didn't you say pi day? Did you just say pi day?
Yes.
I didn't.
Okay.
Oh yeah, we're not supposed to be doing this.
Sorry, this is okay. Come on now. If I look at a cylinder, and this will help us understand this a little bit. Do you guys know the volume of a cylinder?
Yeah, pi r squared.
Volume is pi r squared times h. But I want to give you the idea. I want you to think about this in terms of why. It's the pancake, yes, right? We're going to do. I did, but I want to elaborate this on triangular prisms and so on. It's the same thing. Here's the general form. The volume of any shape is the area of the base shape times the height, right? What is the base shape in a triangular prism? Not a rectangle. A triangle. This triangular prism just happens to be standing on end or laying down. This is your base. You guys see that? Okay? So what you're doing is you find the area of the base, the area of the triangle, and you multiply it by the height. This is the height. You guys remember that? In this case, what's the base? Maybe a rectangle or a square, depending on how you look at it. But you take the area of the base shape and times it by the height. So that principle will be used for today's concepts. What if I wanted this? The volume of this guy. Let's say this is a half circle. What would we say? It would be find the area of what? You find the area of the base. What's the base? Half a circle. So the area of the base is 1/2 pi r squared because it's half of a circle, right? And so the volume would be 1/2 pi r squared times height. And the height is represented by that length, right? Okay? So you have to think of what we're doing today in that context. Okay. Yes.
On the AP test, are they going to give us like equation like that as they do on the SAT?
They'll give you some, but not for this stuff.
They just give you like a
Like they might give you the volume of a cone, but they're not going to give you the volume of a cylinder. All right. Okay. Two concepts to remember. One of them, the area of a region bounded by two curves. Now you guys know this. How do you find the area of a region bounded by two curves? The integral of the top function minus the bottom function, right? Now a lot of you screwed up on the quiz. If you have a top function and a bottom function, that's what you do. But what happens if you have a function here and a function here? Are they top and bottom anymore? No, so you do not say this minus this. You say this plus this, right? Or you turn it on its side, then you can say that minus that. That's putting it in terms of y, right? However you see it's fine, okay? So, example, what is the area bounded by y equals sine of x and y equals 1/3 x squared minus 2? You guys do this quickly. You can use a calculator. I want the area bounded by y equals sine of x and y equals 1/3 x squared minus 2. So graph it, figure out what the upper function is, figure out what the lower function is, find the points of intersection, take the integral. Okay. So there's sine of x. There is 1/3 x squared minus 2. So the parabola is never going to come back down. So that is the only region that those two things will bound. So really we're finding the area of that guy. guys okay with that? Okay, so when you're graphing it, we're only looking at that piece because there's no other piece that is bounded by those two functions. Find the points of intersection. You guys cannot just solve the problem by saying, okay, I'll take the absolute value somewhere. If you're getting a negative number, that means your integrand is probably wrong, or your limits are wrong, or something is wrong. It's not just a matter of, I'm just going to change the sign and I'll be okay. Okay. What is the upper function then?
Sin X.
Let me get there, sorry. Okay, so our points of intersection are, what'd you guys get? I got negative 1.745 and 2.699. So the integral equation to find the area bounded by those two curves is the integral from negative 1.7 to 2.6 of sine of x minus 1/3 x squared plus 2. Why plus 2? Why plus 2 here, not minus 2? Because I'm subtracting this whole thing, so I just distributed the negative into it, right? So maybe that was your issue. And then we solve that, we get 6.843. You guys okay with that? Area of geometric figures. So if you know the area of these figures, you can therefore make those the bases of objects and then find volumes. Okay? So what's the area of a rectangle? Okay, I want you to get away from base times height, use length times width, okay? Even though I put base times height. The area of a triangle is 1/2 base times height, but it should be 1/2 length times width. Okay? The area of a circle is pi r squared. The area of half of a circle is 1/2 pi r squared. What do I got? What's the area of an equilateral triangle? Without looking at my notes already there. You got to, in an equilateral triangle, all the angles are 60, right? So when you cut that one, you get a 30, 60, 90. So the height is the rad 3 side. So if that's an equilateral triangle, where that's the base, how do I find the height? How do I find that height? Divide this into 2, so this would be a b over 2, right? And then what's this length? This is what? It's equilateral. It's equilateral. So what is this? So it's the base.
I said that.
All right, and how are you going to find the height? You can view it as a 30, 60, 90, where this is b over 2 and this is b, right? And so what's this going to be? It'll be b rad 3. So what's the area of that triangle going to be? The whole triangle. 1/2. What's the base? B. What's the height? B rad 3. So this can simplify to rad 3 over 2 times b squared. Okay, that's for an equilateral triangle. Okay, that pops up every once in a while. Yes, it really does. All right.
Get rad 3 over 4 b squared.
That's where I stopped.
Oh, yeah, it's not b rad 3. Who said that?
Dang it, come on, nobody.
Oh, that'd be insane.
It's this times rad 3, not this times rad 3. So this will be over 4. All right. Enough of that. Rad 3 over 4 b squared. Okay. Volume of a solid. So here's where it gets fun. Here's the general rule of finding the volume of a solid. You take, instead of taking the integral of the function itself. Let me go back a second. If I take the integral of f of x dx from a to b, graphically, let's say this is f, what am I finding? I'm saying find the height, right? And take the integral of the height times the width, right? You guys okay with that? This is something a little bit different. We're going to be talking about volume. So instead of taking the integral of the height, we're going to take the integral of the area function, whatever the area is. Okay? We probably should have a picture of this so you can see what it looks like. Okay? Now, it depends on the cross sections. The area is going to depend on what we're slicing it into. And I know you guys are looking at the notes, but let's say let's say this was the base of an object. So it's like a paperweight. There's a flat side to it, right? This is the flat side, okay? And from that, we're going to get some sort of shape coming up out of the top of it, okay? So let's see here. So I'm going to take the axis and kind of turn it on its side, okay? So let's say I slice it. So here, when I was slicing this, I was slicing it into a bunch of what? A bunch of rectangles, right? Here, I'm slicing it into a bunch of rectangles, but now they're going to have a height with them as well. Okay?
How do I draw this?
So here's one rectangle. Just watch it. Watch it, watch it, watch it. Okay? Can you visualize that shape a little bit? You have the base, and then from it, you have squares popping up. Okay? Now, how wide is each square?
The height.
The height of the square, or sorry, the width of the square is only the distance from the red curve to the blue curve, right? And as you go along, that height changes. Does that make sense? And therefore, if this is a square, this length is the same as that length because it's a square, right? Okay. So what we're doing essentially is we're slicing this instead of into an infinite set of rectangles like this, right? We're slicing it. Let me see if I can do this. I don't even know if I can do this. We're slicing it into. How do I want to do this? Let's see. We're slicing it like this. Does that make sense? Yeah. You know, just imagine a bunch of rectangular prisms stacked next to each other, right? So what we're doing is we're adding up the volume of the prisms. Well, this was adding up the area of the rectangles. This is adding up the volume of the prisms. Why? Because we're finding the area under here, or sorry, we're finding the area of this thing, and we're multiplying it by the width. Does that make sense? Just because that's the example.
So like, what if the...
Here's another example. So this is a base, that base on its side, and we have rectangular prisms coming up out of it.
Will it tell you different?
Okay, or squares coming up out of it. Yeah, it'll indicate. Here's another one. Here is semicircles coming up out of it. The idea is whatever the base shape is, you could have anything coming out of it forming different shapes. So if I were to ask you, well, I'm going to give you that information. I'm going to say, what is the volume of the object where the base shape is bounded by the two curves, and you have squares coming out of it, basically. You'll see an example of it in a minute. So, okay, so why do we need to do this? Erica just brought up the point a little bit. Maybe you're an engineer and you're trying to design some really funky shaped building. And you see that in really elaborate architecture stuff. You might need to find the surface area of it. You might need to find the volume of it for different reasons. Honestly, that's above my pay grade. So we're just having fun with it. The other part is this proves, this process eventually will prove like why the volume of a sphere is 4/3 pi r cubed. That kind of thing. So you can go to the theoretical realm of mathematics and say, okay, this is going to help us prove things about volume. Why is the volume of funky shapes like a sphere what is? Why is the volume of a cone 1/3 pi r squared times h? This is why, and we'll get to it when we get there. You got to kind of visualize, it's hard to, but you got to visualize, see these front corners of the square? If you were to connect them with a curve, and then connect these back ones with a curve, You have to visualize that three-dimensional object that's being formed by it. We're finding the volume of a three-dimensional object. Right, I'm trying, I can't draw a three-dimensional figure on a two-dimensional surface and make you go, oh yeah, I get it right away, right? So that's why we turned this on its side, and then we started drawing things coming up out of it. Okay?
So we're gonna
determine the height?
We'll talk about it. What's that?
So we're gonna like take the area of each figure and add it together?
Yeah, basically that's the point. How do we find the area that, listen to the dimensions of this. What are the dimensions of area? What are the units on area?
squared.
Units squared, right? How many dimensions is this? 2. It's a flat surface. How did we find the area? We sliced this into an infinite set of rectangles, and we found basically the height, and we added up a bunch of infinite heights, is essentially what we did. Right? So we took the height, let me break it down a little bit. That's basically what we're doing. We took the height and we multiplied it by the width, and we added it all up, right? Okay? Now think about volume. How many, so this dimension, let's see, what is this dimension? F of x is what? One dimensional, right? What is this dimension? One dimensional. When I multiply one dimension times one dimension, what do I get? I get dimension squared. That's why it's unit squared. That's why we're finding area. You guys get that? Okay, now watch this. If I'm looking for, this is area. If I'm looking for an area. If I'm looking for a volume, what should my final answer be? Cubed. Okay, so I'm going to take the integral, and I'm still going to have this dx out here that's always the same. So this is one dimensional, right? What do I have to multiply it by to get to 3 dimensions? Or dimensions cubed? I have to multiply by 2 dimensions. What object or what concept is a 2-dimensional concept? So we take the area. So we're finding the area of each piece and then adding it up. Does that kind of make sense? A little bit. No, not at all. Okay, good. Let's go on. Okay. Let's look at an actual example here. We're going to look at the same pictures, but we're actually going to solve some stuff. All right. There's the words that you guys are looking for. A solid has a base that is bounded by sine of x and 1/3 x squared minus 2. So it's the same function. That's the bottom of it. Okay? From it, we have square cross sections. So that is one side of the square cross section. So we have squares coming out of that shape. Okay? So that was the first example that we had in this corner here. That are perpendicular to the x-axis. What is the volume of the solid? So, there's the curve again. We have, let's read what it says again. It says it has square cross sections. What's a cross section? Do you guys know what a cross section is from like construction?
Like a slice out of something.
When you slice it up, right? So basically what I'm going to do is I'm going to slice this way. Why slice it this way? Because it says the cross sections are perpendicular to the x-axis. So I'm going to imagine lines that are cutting this way. That's the cross section. You get me? Okay. Now, it says that these are square cross sections. So that means this length, this slice, is the base of one of the squares. Well, what's the height of one of the squares? It's the same thing. It's coming up out of the curve, right? So here's the curvy thing, and then we have a square coming out of it. It's doing this, right? And we have another square over here. Does that make sense? A little bit? Okay. So that's why we have perpendicular cross sections to the x-axis. Do you think we could have perpendicular cross sections to the y-axis? Yeah, we could. We learned how to dealing with terms of y the other day. We'll get there, don't stress. Okay? We have squares coming out of that. Okay? Notice these lines are perpendicular to the x-axis, like I said. Okay? We have squares that are coming out of it. It's not that, it won't be that difficult once we have the equation. Okay? We're going to take the integral. What's the bounds of the integral?
Negative
The same points of intersection that we had before, right? So we're going to take the integral from negative 1.745 to 2.699, okay, of what? What did I say?
Area.
You're going to need the area. Well, what's the area of a square? Length times width. Okay, let me develop that off to the side here. The area of a square is equal to length times width, right? Well, what is the length of this square? How do you determine the length? Here's the curve. Here's the curve. It's doing, where are we? It's like this, right? The square, this is the length of the square, right? You guys see that? Well, how do I determine that length? No, I just want the length. It's the top function minus the bottom function. So then we would say that the length is, what's the top function? Sine of x minus, what's the bottom function? 1/3 x squared minus 2, and put that in parentheses. That's the length. What's the width? It's a square, right? So it's the same thing. So I'm going to take all of this and square it. Now this is the area of the square. So it's the area of the objects, the cross sections, in terms of x. Right? Because these are all x variables. Guys okay with that? Do you agree that this is the area of a square that has a base from here to here? Right. Now what can we say about the area of this square? It's smaller because the length is smaller, right? You get what I'm saying? So now we got to create the equation. The volume equation is the integral of what? The area function times dx. It's always that. When you see cross sections, it's always the integral of the area dx. The question is, what is the area? No, when we're saying we're not finding the area of the square this way. We're finding the area of the square that's coming out of the page. So this is the length, this is the width. Now remember, we're finding volume, right? So we're actually slicing this into a bunch of rectangular prisms where this is the square and this is like the height of the prism. So what we're doing is we're cutting this length infinitely thin. We're cutting the height infinitely thin. That's what the dx is. So this is the area of the base. And this is the height, basically. We're standing it on end. Does that make sense? Okay. All right, do this with your calculator. So we got g of x in this case minus f of x squared. So, do you have sine of x stored in y1?
Yeah.
Do you have 1/3 x squared minus 2 stored in y2? Okay. What are you going to type into your equation? Yeah, so you're not going to write this on your paper, but we're going to say the volume is the integral of y1 parentheses x minus y2 parentheses x. Now what does this represent? Just this piece? No. This piece, y1 minus y2, just represents the distance between the two, right? How do I find the area of the square? I've got to square that, so I'm going to take this.
Is it always that case? You just take that and square it?
And then multiply by dx. No.
Wait, did we actually do y1 parentheses x?
Oh, sorry. So what you're actually typing in, you're going to have double parentheses. So you're going to have parentheses, parentheses, parentheses squared, comma x, comma what? Negative 1.745, comma 2.699, close parentheses. Those two. No, I don't think you're. I got 1, 2, 3, 4 opens. 1, 2, 3, 4 closes. Yeah. All right. What do you guys got? 13.328. Okay. So again, like I said, this is g of x minus f of x is the length of the square. We're squaring it because this whole thing gives me the what? The area of the square. So what did we just find? We found the area of this square, right? It's standing up. right? Then when I multiply it by dx, what's dx represent? Dx represents the width, right? So we just multiplied it by dx. And we found the volume of that thing, right? And when we take the integral of that, we're finding the volume of all the prisms added up.
So basically, if they ask for squares, like you can just do it like normal and then just square it.
Aw.
Yeah, but don't try and look for shortcuts because you're not always going to have squares.
Well, no, that's what I'm saying.
Let's-
If it asks for
Yeah, in a sense, you got to think, okay, what is the equation for the area? It's length times width. What is the length? The length is y2 minus y1. Okay, I got to square that because it's a square. If it was something else, I couldn't square it. I would if it was a rectangle, then I'd multiply it by something. And that's for later, okay? Okay, so is that what you said, 13.328? Yeah. Okay, going on. Let's try another one. Same function in your calculator, so don't delete that. Let's look at the cross sections being what? Wow.
What?
Points of intersection of a... Oh, we're not looking at an example here. I'm just going over a summary of it. Okay, never mind. So A is the area of the cross section, and A and B are the points of intersection. So then the volume is equal to the integral of the area dx, because the area times the width is what? Volume. And then the integral sign means add up all the volumes. Okay? That would be perpendicular to the x-axis. What would it look like for perpendicular to the y-axis? For the y-axis, what would it say?
Integral.
From A to B, where A and B are what kind of numbers?
Y.
Y values of area in respect to y dy. That's all. Okay. All right. No, I just said that.
People that never take those.
They must cheat.
I don't like that. I'm just gonna. I wish my copy was taken. Or at least have a record button.
All right. Okay, here we got what? What kind of objects? That is triangular cross sections. Now, what's the area of a triangle? 1/2 base times height. What is the base of the triangle? Let's look at that for a minute. A of x, d of x. So the area of a triangle is 1/2 base times height. So that's going to be 1/2 of, what's the base? That's going to be the upper function minus lower function. So in this case, we would say y1 minus y2. That's the base. What's the height? It depends what kind of triangle it is. What if I just said the height is always 5?
Wait, yeah, how do you
Then it would.
You can't. I would have to give you more information. Here's a couple examples. What if I said I wanted triangle cross sections perpendicular to x-axis, so triangle cross sections perpendicular to x-axis, the 1/2 base is that, you got that, right? What if I said where the height is 5?
multiply by 5?
What if I said this is where the height is 5? What if I said the height is 5 times the base?
Then you have to use y.
Then the area of the triangle would be 1/2 of y1 minus y2. That's your base, right? What's your height? 5 times y1 minus y2. You guys okay with that? Okay. There's a lot going on here. All right. 1/2, ooh, what kind of triangle would that be? If it was 1/2 y1 minus y2 times y1 minus y2.
Both the sides would be equal.
That means the base and the height are congruent. So maybe if it was a right triangle, it'd be isosceles. It wouldn't have to be. It could be any triangle where the base and the height are the same. But isosceles, I guess, is what I was thinking there. So there's your base, there's your height, and then dx is your width of the triangular prism. All right, let's look at an example here. Try this one. What's wrong? Oh, new equation. Let f of x equal negative 1/2 x plus 4. What is the volume of the solid whose base is bounded by f of x, the x-axis, and the y-axis? Why should it be a triangle? What is the base shape? Triangle, because why? Not because of the cross sections here. Yeah. If I'm going to graph f of x, that's going to be up 4 and then down 1 over 2. So something like this. Okay. Now we want the region that's bounded by what? The x and y axis. Pay attention to this. This might open your eyes a little bit. Which way is the perpendicular cross sections? Perpendicular to the... So this is your slice, right? Okay. And from this slice, we have what kind of shapes coming out? Triangles. What kind of triangles? Isosceles triangles. So it would be something like this, where these two are congruent and that's a right angle. You guys see that? It could be the other way. Keep it? Okay, I'm glad, because these pictures are... Why the two what? Okay, these two could be the isosceles sides. Yeah, I don't know. I'd have to give you more information on those. It would say where the base and the height are congruent or something like that. All right, what would the equation be? It'd be the integral of, from where to where? 0 to what? From here to here, right? What is this point? How do you know 8? Because that's where the negative 1/2 x plus 4 crosses the x-axis, right?
Yeah.
What would you do? You set f equal to 0. Okay, so you get 8. Of what? What is your area function? What's the area of that isosceles triangle? Let me write this off to the side. Area is equal to, what's the base? What is this length? What is it? Negative 1/2 x plus 4. It's the function's height, right? This represents the height, right? Okay. So this length is f of x. How tall is this? Negative 1/2 x plus 4, because it's isosceles. So that's your area formula. You could simplify that by saying 1/2 of negative 1/2 x plus 4 squared, and then dx.